In my daily life, I effortlessly execute a large number of different movements without thinking about it. From the simple act of grabbing a cup of coffee to maneuvering through a crowd as I stroll through the city. These seemingly effortless movements showcase the ability of our bodies to act intuitively. There's a seamless connection between our mind and our actions, between our brain and our muscles and bones. My name is Kim Adams, and I'm the team manager of the 9th team of Project March. So now, I want to ask you all to think for a second about all the different movements you performed to reach here today. Perhaps you arrived by train, by car, or even by foot. Upon arrival, you ascended stairs, maneuvered through the aisles, and eventually settled into your seat. It's most likely that almost everybody didn't consciously think about all the different movements your body performed. In contrast, there are people who face the challenge of navigating life without the same abilities. For example, people with paraplegia, who are permanently wheelchair-bound. Paraplegia is a medical condition characterized by the loss of movement and sensation in the lower part of the body, caused by damage to the spinal cord. This damage leads to a disruption of the signal transmission between the brain and the lower limbs. The degree of impairment varies depending on the height of the injury. In the Netherlands, there are approximately 15,000 people permanently wheelchair-bound due to a spinal cord injury. Worldwide, this adds up to about 9 million people. Being permanently wheelchair-bound affects people's daily life drastically. For these people, it's no longer possible to easily ascend or descend stairs or take the train. Each movement requires much more time, effort, and preparation. Each movement is a unique challenge, a unique obstacle in their daily life routine. Beyond its evident impact on mobility, paraplegia can lead to several secondary effects on the physical health. First of all, it can negatively affect the muscle and bone strength. The lack of weight-bearing activities of the legs can lead to loss of bone density and an increased risk of osteoporosis and fractures. Furthermore, paraplegia can result in decreased control over the bladder and the bowel. And it can result in reduced blood circulation in the paralyzed parts of the body, resulting in an increased risk of thrombosis. One other aspect we shouldn't forget is the impact of paraplegia on the mental well-being. Adapting to the physical changes, overcoming challenges associated with paraplegia, and the inability to maintain eye-level contact with the people around you can significantly influence the mental health. For almost 9 years now, the members of Project March have been pushing the boundaries of exoskeleton technology, with the goal to improve the quality of life of people with paraplegia. So, the key question is, what is an exoskeleton exactly, and how can it impact the lives of these people? Well, an exoskeleton is a powered robotic suit attached to the outside of the body that takes over the muscle, nerve, and bone function of the lower part of the body. The exoskeleton enables someone with paraplegia to stand up and walk again. Apart from the improved mobility, regular standing and walking facilitated by the exoskeleton can help reduce some of the secondary health issues I mentioned before, like the decreased bone and muscle strength, the affected blood flow, and the impaired bladder and bowel function. Moreover, the ability to stand and walk can have a great impact on the mental health. It promotes a sense of empowerment, reduces the feeling of dependency, and most importantly, enables individuals with paraplegia to stand eye to eye with their loved ones again. About 6 months ago, the 9th team of Project March entered the Dream Hall for the first time. A group of 28 extremely motivated students with different nationalities, interests, and backgrounds. We paused our studies for a whole year to work towards one common goal: designing, building, and testing an innovative exoskeleton in only 1 year time. But our team did not embark on this challenge alone. From day one, we have been working together with our 29th, and I would dare to say, our most important team member, the new pilot of Project March, Daan van der Heijden. Daan is, yeah. Daan is 31 years old and has a T5 lesion, which means that he's paralyzed from below his chest. Daan is a professional wheelchair basketball player and plays for his club in Osnabrück in Germany. With his top sport mentality, he's mentally very strong and extremely motivated to explore the limits of exoskeleton technology with us and showcase our innovations to the world during the Cybathlon in October. For the past 8 years, the members of Project March have been making great technological innovations, from brain control of the exoskeleton using EEG, to walking on different terrains, and last year even balanced walking. This year, we take the next step towards daily use of exoskeleton technology, combining all innovations from the past 8 years into one versatile exoskeleton, and innovating even one step further. Building an exoskeleton that is capable of executing all those different movements you perform during the day. We aim to empower individuals with paraplegia by giving back the control over their daily life activities.
All right. Quite a lot of people, if I'm honest. Does anybody have any idea how many people are in this room right now? Hands up for over 200. 300 even? At this moment, we're sitting in a room with 586 people, each with their own unique anatomy. This also applies to the 9 million people with paraplegia. Every patient is different, which means there's not one perfect treatment that works for everybody. There are multiple methods which can be used as treatment based on a specific situation. Surgery, which can be done to treat muscle injuries. Medications, which can be addressed to reduce the risk of infection. Or physical therapy, which can help to regain as much function as possible by teaching our brain and body to work around the injury. So, why? Why build such a complex innovation? Because none of these treatments give you back the ability to get up to eye level, thus facing others without looking up, and do your daily activities without the use of a wheelchair. For that, we need something with a larger freedom of movement. Something that an exoskeleton can give us. Good evening, everybody. My name is Stijn Huytega, and I'm the project manager of Project March 9. And we believe by improving exoskeleton technology, we can help people with paraplegia to do their daily activities without boundaries. In the year 2015, there was a group of students that started a dream. With no team before them, and research done only by other projects, they built the first prototype of Project March. March 1 started this incredible journey with a vision that's still being believed in today, 9 years later by our team. Since the beginning of Project March, we have been tied to the Cybathlon. And the Cybathlon is one of the largest bionic competitions in the world. It involves 8 different competitions, all focusing on different assistive technologies. for example, exoskeleton technology. And teams will gather and compete against each other on an obstacle course. And through the obstacles and its competitive platform, the Cybathlon directs the focus of the innovation towards these daily activities. Every 4 years, the Cybathlon occurs in Zurich, in Switzerland. And this year, we have the honor to participate. In October 2024, the team will travel to Zurich with our exoskeleton and show the world what Project March brings to the table. Each year, Project March has a completely new team, with new ideas and a new goal. This way, you refresh the process and create the opportunity to step out of the tunnel vision. In these last 8 years, Project March has achieved many unique innovations, where the first few years focused on creating an exoskeleton with working core functionalities, such as making a simplified prototype with operating joints. But eventually, the project evolved towards a level where the focus could be shifted to even more complex innovations. Think of walking over uneven terrains, thus making it able to go outside. Having a fully dynamic, generated walk by finding the most optimal foot placement for each step. And walking balanced, without the use of crutches, to give back even more freedom. The area where opportunities lie is by creating an exoskeleton capable not only of restoring these single functionalities, but also making sure that it can actually facilitate the basic daily life activities. So at the beginning of the year, we set a goal for ourselves, something to focus on. A daily reminder that every ounce of effort that we put into this project brings us one step closer to achievement. Project March 9 will build an exoskeleton that will complete all 10 obstacles in the Cybathlon 2024 within 10 minutes, focusing on the reliable performance of the exoskeleton as well as the pilot with a motivated team. To achieve this goal, we have a few steps to take. Firstly, apply all obtained knowledge from our predecessors and integrate them into one coherent version. And secondly, dive into the obstacles themselves. As outlined in the team goal, the Cybathlon consists of 10 obstacles, each mirroring everyday activities such as ascending and descending stairs, opening and closing doors, or stepping over boxes. In comparison to the previous edition, there are 4 more obstacles added to the course. And furthermore, the former obstacles have been adapted, which means we have to innovate even further beyond what previous March teams have already developed. To make things even more challenging, we do not only have to complete the 10 obstacles, but we're also time-bound. We have to accomplish them all in a row within a time frame of 10 minutes. This forces us to come up with an airtight strategy on how to navigate through the obstacles, but also how the pilot can best control the exoskeleton. Simply put, we cannot afford to lose even 1 second. As you may understand, our team goal is not really an easy task. Therefore, I'm really happy to work on this project in such an amazing and dedicated team, starting as 28 strangers to each other in August 2023, but now all working together to complete those 10 obstacles. So now you know a bit on what we're going to do this year, so let's not keep you waiting on how we're going to do this. Hopefully, we warm you a bit up for the next part, the design of the new exoskeleton of our team, Project March 9. Thank you all.
Wow, what an amazing exoskeleton. You might be wondering, how does it actually work? How can this exoskeleton complete all the 10 obstacles within 10 minutes? I am Max, and I'm the Chief Engineer of Project March, and today I'll walk you through the key components that make up the exoskeleton. The functionalities can be compared to those of the human body. Just like our bodies have bones and muscles to make sure that we can stand and move, the exoskeleton has joints and a frame to achieve the same goal. The frame can be seen as the bones of the exoskeleton. It provides the pilot with a strong and stable base to make sure that he stays upright. But how does the frame actually move? For this, we have our joints. These can be compared to the muscles of the exoskeleton. We have two different types of joints. First of all, we have the rotation joints. These allow for a bending movement similar to a hinge. The first one is located in the knee. This one makes sure that the pilot can bend his leg. The second one is in the hip. This allows the pilot to move his entire leg up and down. Aside from rotational joints, we also have the linear joints, which allow for linear actuation. The first one is again located in the hip, but this time to make sure that the pilot can move his legs sideways. The second one is located in the ankle, to make sure that the pilot can move his foot up and down. All of these mechanical components also need to be produced. I can proudly say that the March 9 features the most self-produced parts out of any March exoskeleton. Once our exoskeleton is walking, you will likely not see much of these mechanical components. That is because they're hidden by our covers. These make sure that our mechanical and electrical components stay well protected. However, functionality is not all. For this year, we've decided to partner with one of the oldest Delft Blue companies to create a unique design for our covers. This makes sure that we stand out at the Cybathlon not only for our innovations, but also for our cultural connections. To discover the final designs, don't miss out on our reveal in July. Now that you have a basic understanding of the key mechanical components, let's see how the pilot brings it to life. Our journey starts with the input device, conveniently located on the crutch of the pilot. Here, he can select his desired walking pattern with the press of a single button. He can first choose where he wants to walk forward, take a smaller step, or stop the exoskeleton. This year, our new version now allows the pilot to easily switch between all the different walking patterns. And the input device can now be detached from the crutch to make sure that the pilot can still control the exoskeleton when he's walking without crutches. Once the pilot selects a walking pattern, a signal is sent to the backpack. This is a crucial and central component of our exoskeleton. It houses all the crucial components that bring the entire system to life. Here, nestled amongst the other technology, lies our power distribution board. This component receives the energy from the battery and then seamlessly distributes it throughout the exoskeleton. Imagine it as a conductor in an orchestra, carefully coordinating the flow of power. Just as a conductor ensures that each musician plays the right notes, the power distribution board makes sure that each component receives the right amount of energy. The true magic unfolds within the main computer. This can be seen as the brain of the exoskeleton. When the pilot selects a walking pattern from the input device, it sends a signal to the main computer, which then calculates the required sequence of movements. Using advanced algorithms and real-time sensor data, it then finds the movements needed for each individual joint. Now the only thing that's remaining is that the computer needs to tell joints what to do. However, the computer cannot directly talk to the joints. For this, it needs an extra electronic component in between. These are the so-called mode controllers. When the computer sends a signal, it sends a signal to the mode controller, which then passes them along to the joints, which can actually move. And just like that, the circle closes. The pilot's desired walking pattern, chosen with the press of a single button, sends a signal to the main computer, the brain, which can calculate the required sequence of movements needed for each individual joint, which can pass the signal to the mode controllers, and which then in turn let the joints actually move. However, completing all the 10 obstacles within 10 minutes demands even more innovation. To delve into these exciting advancements, I'm thrilled to announce two of our engineers to the stage.
Thank you, Max, for that nice introduction of our EXO. Now that you hopefully have a better understanding of how our EXO generally functions, we would like to dive deeper and show you where we, the 9th Project March team, have innovated. My name is Femke Buijks, and I'm this year's lead software engineer.
And my name is Tom de Koning. I'm one of the mechanical engineers.
Let us, just as Max showed us, follow the example of how a command from the pilot travels through the EXO and show you along the way where we have innovated.
This year, our primary objective is to develop an exoskeleton capable of replicating human-like navigation in daily activities. As you and I walk around, our brains are continuously evaluating where we can and cannot safely place our feet, using our eyes to assess our surroundings. We gave the EXO depth cameras, serving as its eyes, so that it's able to gather visual cues from its surroundings. And by integrating these cameras, we aim to give the exoskeleton the intuitive ability to select safe steps, enhancing its adaptability to unpredictable terrain and ensuring efficient execution of daily tasks. Previous teams have also used cameras to dynamically determine stepping points, but March 9's team goal is focused on speed and efficiency. Thus, besides creating our own implementation of the computer vision algorithm, we aim to increase the speed of the code. In the past few months, we have been able to find methods to increase both speed and efficiency by restructuring the data coming from the cameras. This way, the image content from the cameras is organized and stored in a different format, allowing for easier manipulation by the main computer. One key focus of the eyes of the exoskeleton is the identification of flat surfaces deemed safe for the EXO to step on. With our algorithm, we are able to identify surfaces, so-called planes, and all their characteristics, such as shape, color, and orientation. To determine the optimal stepping point on those planes, a footstep planner algorithm is implemented in the main computer. The footstep planner algorithm takes factors such as the shape and proximity of the present planes, ensuring both feet of the pilot can fit securely, while also taking into account the range of motion of our pilot. Once a suitable coordinate is found, it is later used to place the desired step. Important to note here is that our pilot is still in complete control of the EXO. He will still indicate when he wants to move and what kind of movements he wants to make. The purpose of the computer vision algorithm is to ensure that these movements are carried out safely.
In replicating human behavior, this year we also prioritized the need for precise feedback and control mechanisms in the EXO. The key to achieving this lies in comprehending and mimicking the way humans perceive and interact with their environment. Human motion is defined by changes in joint angles over time. Take, for example, the knee joint angle, which represents the angle between the upper and lower leg orientation. As you walk around during your day, the orientation of your leg parts is rarely something you would think about, But to construct a walking pattern in an exoskeleton, it is crucial to accurately define these joint angles at the correct moments in time. To do this, we require an understanding of the initial standing position of our exo and its position relative to the world. Much like how humans use their senses, such as vision and touch, to navigate, the exo must process information from the outside world to seamlessly interact with its environment. To enable this effectively, an algorithm called state estimation is used, which determines the exact configuration or state of all the joints in the exo, using all available sensor data and using knowledge of our dimensions of the exo. This algorithm thus requires translation of data coming from sensors, such as sensors measuring force, rotation, and temperature, so that it can be used by the exo. This data, however, is inherently noisy, as we are collecting so much of it, and as we are working with a live pilot in our exo. Much like the human brain's sophisticated filtering of sensory input, the exoskeleton utilizes a filter, a so-called Kalman filter, within its state estimation algorithm to enhance the reliability of the data. This filter combines noisy data with past trends and a dynamic model of the exo, resulting in accurate state estimation. Knowing the exact position of the exo with respect to itself and the outside world enables real-time decision-making regarding the movements that are necessary to reach a specific destination. This destination, as you may recall, comes from our computer vision algorithm, showcasing the extensive computational capabilities of our exo. Once the current configuration of the exo is known and the desired joint angles have been computed, this information travels through the exo's nervous system, or its wires, towards the joints.
The joints in the exoskeleton, however, are not able to directly interpret the joint angle data coming from the main computers. So, the motor controllers serve as converters to give commands to the joints which they can understand. They translate joint angle data to electrical current. As our goal this year is to complete 10 obstacles in 10 minutes at the Cybathlon, we must ensure a fast-moving and dynamic exoskeleton. This includes fast communication between all electronic components. Not only the communication between the motor controllers and the joints, but also the communication between the motor controllers and the main computer. In previous years, the motor controllers and the main computer in the exoskeleton were not able to directly communicate with each other. To simplify, think of it as all electronic components in the exo speaking a different language. And to allow for communication between the motor controllers and the main computer, an additional translator was needed to translate the data. This resulted in extra hardware being added to the exo, notably decreasing its reaction speed. To increase the communication speed, the previous team has changed the hardware connections. This helped somewhat, but this year we aim even higher. We have designed our own custom motor controller, which we call the M-Drive. The M-Drive is inspired by motor controllers that were used in previous years, but it is special since it's able to directly communicate with our main computer. Think of it as if we taught the M-Drive a new language, and so there's no longer need for this additional translator. This increases the communication speed significantly. The joints are thus able to execute commands coming from the main computer through our motor controllers much faster, meaning our exo can react quicker, move dynamically, and seamlessly synchronize its movements with the pilot's intentions. So, after a signal, such as the desired joint angle configuration, has been translated by the M-Drive, the correct current is sent to the joints, resulting in the desired movement.
These joints have also been redesigned this year, as a key focus of our design challenge has been to enhance the efficiency of our exo by reducing its overall mass. As our pilot has a relatively high lesion and needs to navigate through many obstacles, we demand a lightweight yet robust exoskeleton for optimal performance. One key aspect of this weight reduction has been the redesign of the rotational joint, which is responsible for both hip and knee flexion and extension. This innovation involves a significant departure from previous year's designs, as the motor and the output are now stacked vertically on top of each other instead of being positioned side by side. This adjustment allows for a direct connection between the motor and the output, eliminating the need for an additional transmission step in between. The outcome of this is a 700-gram weight reduction per rotational joint, translating to nearly 3 kilograms across the entire exo, which is a serious weight reduction that will help the pilot navigate the challenges. Another big weight saver this year has been the new leg frame design. For the first time, topology optimization has been used to design these frame parts. Topology optimization is a technique that explores various design possibilities to construct frame parts that are maximized in their strength while minimized in their weights. This technique uses algorithms to strategically remove parts of the frame while still ensuring it can withstand the forces that the exo will encounter in the real world. The result of this, a significant 40% reduction in total mass of the leg frames, contributing to a lighter and more agile exoskeleton, perfectly aligning with our mission of completing the Cybathlon.
And to complete all challenges in the Cybathlon, we must balance the exoskeleton without using crutches. To help with balance, we have introduced a new joint in the March exoskeleton this year, the ankle inversion-eversion joint. To achieve a balanced walk, the pilot must shift his weight to his stance leg every time he takes a step. This is where the ankle inversion-eversion joint helps. With this joint, the pilot is able to sway from side to side. This joint also helps with keeping the feet flat during sideways walking and keeping the pilot more upright on the tilted path obstacle. In the exoskeleton, this joint is located behind the heel of our pilot. And in contrast to all other joints, this joint is passive, which means that no motor actuates it, and thus we cannot directly control this joint. So, how do we make sure the exo and the pilot remain upright? The desired characteristics of the joint are achieved by tuning a spring mechanism in the joint itself. This spring mechanism consists of 2 springs that push a small wheel onto a profile. And when the joint rotates, this wheel rolls along the profile. So, dependent on the angle, a specific force is applied. By changing the tension in these springs, or the shape of this profile, we can tune the characteristics of the joint itself. And determining these characteristics proved quite a challenge. As I previously mentioned, this joint helps with weight shifting, sideways walking, and walking on a tilted path. And it has to be suitable for all these scenarios. So, we decided on a joint that would help keep the pilot balanced when he's standing on one leg, but is otherwise not producing force. And we can visualize this with the potential energy of the system. Please bear with me. Let's say the ball on the curve represents the ankle joint angle on the right. And rolling the ball on the curve will represent what the joint will do. As you can see, if we move to the left, we can roll the ball to whatever position or angle we want. And the joint doesn't really do anything. This helps with sideways walking, for example. Whereas if we move to the right, the ball falls down the bottom. At this specific angle, the pilot is balanced on his stance leg. If we now move the ball left or right, it will always return to the bottom, meaning that this mechanism can deal with the disturbances that are present in the real world. And thus we are able to balance our pilot.
You have just seen 5 of the innovations that we've been working on this year. Naturally, these are not the only features we have been developing for the past months. We, Tom and I, are just 2 out of 20 engineers working on this team. Across the 3 departments, our engineers dedicate all their time and effort to creating a state-of-the-art exoskeleton that will bring us one step closer to the finish line of the Cybathlon. To conclude this presentation today, I would like to give the word back to Kim.
Performing so many different movements on a daily basis asks a lot from our body. We have to ascend and descend stairs, walk balanced, bend over or squat when we drop something, and walk dynamically, adapting our walking pattern to our surroundings. Developing an exoskeleton capable of executing all those different movements is quite a unique challenge. To face this challenge, we have made many advancements, additions, and alterations. The team focused on implementing a new ankle joint for incline walking and enhancing overall balance. We redesigned the frame and the rotational joint to reduce weight. Our embedded engineers have designed a custom motor controller to optimize communication speed. On the software side, we optimized the state estimator to be able to determine the state of our exoskeleton. And we implemented cameras to sense the surroundings and walk dynamically. However, these innovations are not the only things we are working on this year. Building a complex machine, such as an exoskeleton, from scratch requires an immense investment of time, effort, and energy. We will only build a functioning exoskeleton capable of completing all the daily life challenges of the Cybathlon when everything is considered and all different parts are well integrated with each other. To ensure the success of our many challenges, we are fortunate with an exceptional team of supporters. I want to take a moment to express our gratitude to all of our partners, whose contributions are vital in enabling us to develop our exoskeleton. By providing components, funding, and consultancy, you play an extremely important role in our year. And you make sure that we can innovate and improve exoskeleton technology each year again. In addition to our partners, we are blessed with a highly dedicated community of former March members. We want to thank you for your loyal support throughout the year. You are always there for us to advise or support us through the many challenges we encounter. 6 months ago, we were total strangers to each other. And now we are a close team and a group of friends working together on this amazing journey. I'm extremely proud of this team, and it's a blessing to work with such a highly motivated group. So now, to end the evening, I want to introduce you to them, to the members of the 9th team of Project March. So please welcome to the stage our mechanical department with Jet, Jesse, Tom, Kiki, Anna, Sjoerd, and Michelle. Our software department with Femke, Alexander, AJ, Andrew, Nike, Mick, Martijn, and Pleuntje. Our embedded and electrical department with Sorana, Kim, Jikke, Jort, and Ruben. Our operations department with Stijn, Charlotte, Daan, and Jiska. And our management team with Stijn, Thibaut, and Max. And last but not least, our pilot, Daan. We will now focus on producing and testing our final exoskeleton design. And by the end of July, Daan will be able to tackle some of those daily life obstacles with our exoskeleton. We want to thank you all for joining us tonight, and I would like to invite you for a drink with us in the foyer. We are ready for the next step. We are Project March. Thank you all. Oké jongens, kom maar. Thanks. Ja. 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 Yes. Nou, mooi. Vond je het goed? Ja. Was het wat? Was het wat? Goed zo.
Could you be mine? If we ain't got love, then we got nothing. that we got nothing. All my life, I've been running around, I've been trying to find